Where does the delicate lacy structure of frost on a window come from? How do atoms arrange themselves into facets on a crystal? What happens inside ice when it melts? These are hard questions to answer because each of these systems involves so many different tiny atoms. There are a whopping 100 sextillion molecules in just a gram of water. So it's not really possible to just put them all under a microscope and watch what happens as they crystallize or melt. Instead, we have to get creative to understand the microscopic motion of the matter that makes up our world. One tool we have is a computer. Since there are too many atoms to understand all their interactions, we can come up with clever ways to model them as they zoom around. These models are called simulations, and the set of steps we need to achieve them are called algorithms. One of the first people to make these kinds of simulations possible was a physicist named Arianna Wright Rosenbluth. The key idea behind the simulations that she programmed is that instead of keeping track of all the ways an atom can move, we only really need the ones that are most likely. The algorithm that she wrote and programmed in the 1950s is still hugely important to science today. In fact, Dr. Rosenbluth was instrumental in changing the way we think about probability, statistics, and how we know what we know. Arianna Wright Rosenbluth was born in Texas in 1927. As a young woman, she loved reading, especially books like the Wizard of Oz series, and fencing. She fenced competitively throughout college, won duels against both women and men, and even qualified for the Olympics, twice. Arianna was also a brilliant student. She graduated from college when she was only 18 years old, with honors in both physics and math. After college, she moved to Boston to continue her education at Harvard University. At the time, there weren't many women in her department. Arianna was even told by one professor that he wouldn't accept any women into his lab. But she kept learning and doing research, and at the age of 22, she became the 5th woman ever to receive a doctorate in physics from Harvard. When Dr. Rosenbluth was starting her scientific career, there was one topic in physics that loomed larger than any other: how to harness the power of atoms. Just a few years prior, the Los Alamos laboratory had developed the world's first atomic bombs, weapons that were used in deadly attacks against the cities of Hiroshima and Nagasaki. But that was unfortunately just the beginning of a race to develop more and more deadly weapons, exploiting this atomic power. Arianna joined Los Alamos as a staff scientist in 1951, along with her husband, Marshall Rosenbluth. At the time, the lab was focused on developing new types of weapons based on fusion, merging 2 atoms into one, instead of fission, splitting an atom into 2. Arianna Rosenbluth did some work verifying calculations for fusion-based bombs, but soon started focusing on a new instrument that was being built at the lab, a computer called MANIAC-1. MANIAC-1 was what was called a fast computing machine. It was massive, weighing over 1,000 pounds and incredibly temperamental. Any directions given to the machine had to be translated onto punch cards, which were sheets of paper with holes punched into them in a sequence that the computer could understand. Dr. Rosenbluth was one of the few people at Los Alamos who knew how to code and use the machine. But what's more, she was also a physicist who could develop new algorithms for the machine to implement. The combination of these skills would prove really important for her next project. Arianna and a team of other scientists wanted to figure out how to calculate what's called an equation of state. This is an equation that describes how different variables we can measure, like temperature, pressure, or volume, depend on each other in complex systems of many particles all moving around. These kinds of equations are crucial for a field called statistical mechanics. We can think of statistical mechanics as the connection between things that are very tiny and behavior that we can see. It describes how a lot of small things, all moving together randomly, can come together to act in a predictable way. Dr. Rosenbluth and the other scientists wanted to see if this new computer could help them understand messy systems with lots of atoms. To simplify matters, they pretended that their atoms were instead small circles. They wanted to see if they could model these atoms undergoing an important physical process called a phase transition, like melting from a solid to a liquid. But that simulation demanded a lot of memory and computing power, more than the rudimentary MANIAC had. They needed a clever trick to solve these equations without simulating the motion of every single particle. The team decided to use a method called a Monte Carlo algorithm to solve the problem with randomness. Monte Carlo is a famous casino where games are played based on the roll of a die or the random motion of a ball. While Monte Carlo algorithms do use probability to solve problems quickly, not all guesses are equal. The algorithm succeeds by prioritizing the best guesses. To use these methods for their atomic problem, Dr. Rosenbluth and the team simulated a bunch of configurations of their circular atoms. Although they used random sampling to help them pick these configurations, they looked more at configurations that have a lower energy and are therefore more likely to exist. Their algorithm goes like this. First, simulate a random snapshot of the particles and calculate its energy. If the energy is lower than the previous state, accept that snapshot as a step in the simulation. And if the energy is higher, randomly decide whether to accept or reject this snapshot, but weigh that acceptance probability based on how low the energy is. This penalizes the more rare high-energy states and focuses the simulation on the most likely situation, allowing simulations of lots of particles to be run much more quickly and efficiently than ever before. Arianna Rosenbluth wrote this algorithm into computer code and figured out how to make it work. That implementation became known as the Metropolis algorithm after the first author listed on the paper, but Dr. Rosenbluth's contributions are so important that some have proposed renaming it to the Rosenbluth algorithm. The method is part of a larger family of algorithms called MCMC methods, or Markov chain Monte Carlo algorithms. Now that we have even more powerful computers, they've become incredibly important statistical tools. Even though they were originally written to model atoms, MCMC methods are now used in almost every field of science, from biology to astronomy to data science. Arianna Wright Rosenbluth's career in physics was, unfortunately, a very short one. She left the field after having her first child, since, at the time, it was expected that women would stay at home and focus on family life. But even though she was only a professional scientist for less than a decade, the effect that she had was massive. In her effort to answer a simple question of how solids melt into liquids, she developed one of the most important computer algorithms of all time. The legacy of her research has changed the fundamental way scientists think about probability and inferring truth from data. To date, more than 50,000 scientific papers have cited the influence of her work on the Metropolis Monte Carlo algorithm, an algorithm that we may someday remember as the Rosenbluth Monte Carlo algorithm.